lecture number 3 of HVDC and FX. So first lecture we learn about the limitation of HVAC, advantages of HVDC, disadvantages of HVDC, and the main objective of HVDC. And the types of HVDC links. Normally 3 types of links is there: monopolar link, bipolar link, and the homopolar link. In second lecture, we cover the principal parts of HV transmission systems, right? Use of converter, filters, smoothing reactor, electrodes, links, and the last one is a circuit breaker. Okay. So in this lecture, first this is the diagram of HVDC bipolar links, which is present in India. It is between Riyadh and Delhi. It has a 750 megawatt capacity. It is a bipolar link, and therefore it is multiplied by 2. Second one is a Chandrapur and PAD. It is also 750 megawatt links is there. Third one is a Telcher and Kolar. Between Telcher and the Kolar, it is a 1000 megawatt. Right. So the HVDC in India bipolar links are this one. Okay. Similarly, the asynchronous links in India, it is Vindhyachal, north to west. The capacity of that is 250 megawatt. It is again bipolar. Chandrapur, west to south, 500 megawatt. VZ, east to south, 500 megawatt. Sasaram, east to north, 500 megawatt. Here is there. And back-to-back HVDC, right? This is also the back-to-back. VZ1 and VZ2, right? 500 and 500 megawatt capacity is there. So now we start the analysis of three-phase Fourier bridge converter, right? So the converter performs the AC to DC conversion and provides the means of controlling the power flow through the HVDC link. The measurement elements of the converter are the valve. This is called the valve. And as you know that the valve, it is a number of coils that are connected in a series and parallel. And the second major element of the converter is the converting transformer. Okay. So the valve bridge is an array of high voltage switches or valves that sequentially connect the three-phase alternating voltage to the DC terminal. So the desired conversion and the control of power are achieved with the help of this valve. The basic model of an HVDC converter is a three-phase full-wave bridge circuit, which is also known as a gate bridge. So before starting the analysis of a three-phase full-wave bridge circuit, we will make some assumptions. So the first assumption for the gate circuit, first assumption is the AC system, including the converter transformer, may be represented by an ideal source of constant voltage. Ideal source of constant voltage and the frequency. In series with a lossless inductance. This is your first assumption, right? Before starting the analysis of a converter circuit. The second assumption is the direct current is constant and the ripple free. The direct current or DC current. DC. Right. The direct current is constant and ripple free. There is no ripples present in a DC current. Ripple free. Third assumption is The walls are ideal switches. Ideal switches with zero resistance, with zero resistance when conducting, when conducting, and infinite resistance and infinite resistance when not conducting. Right. So these are the basic three assumptions we made right before starting the analysis. Okay. So now we start the analysis of a three-phase Fourier bridge rectifier. This is a basic waveform of three-phase bridge rectifier. Here the A phase is there. This one is your A phase. This is your B phase, which is a 120-degree delay, and this is your C phase, which is also a 120-degree. So in one cycle, right? Suppose we start from here. So from this to this is your complete one cycle. So during this cycle, here the 6 pulses generated 1, 2, 3, 4, 5, and 6. Right? Okay, and therefore it is called the 6 pulse current. Let the insertion line to neutral source voltage, right? It is called the EA is equal to EM cos omega t plus 60. Why we take omega t plus 60? Because the EA is peak here, right? At 60 minus 60 degree. So when we take the cos term, right? So it is become plus 60, and therefore we write E is equal to EM cos omega t plus 60. Now what? The B phase is 120 degree apart. So EB is equal to EM cos omega t minus 160, and EC is equal to EM cos omega t minus 180. What is EM? EM is a peak voltage. Similarly, the line-to-line voltage EAC, it is EM minus EC. So when we subtract these two equations, EM minus EC, we get this equation, root 3 EM cos omega t plus 30. Similarly, EBA is equal to EB minus EA is equal to root 3 EM cos omega t minus 90 degree. And ECB, it is EC minus EB is equal to root 3 EM cos omega t plus 150. You can also do ECA, EAB, and EBC, right? So throughout the chapter, I will perform the analysis or derive all the expression for this EAC. Okay, so remember that things. In this figure, the cathodes of wall, this one is a cathode of walls, this one. Okay, 1, 3, and 5 of upper row are connected together. Therefore, the phase to the neutral voltage of phase A is become more positive than the voltage of the other two phases, 3 and 5. The wall start conducting. Means these phases become more positive compared to the B phase and C phase. At that time, the wall 1 is start conducting. The common potential of the cathodes of the three walls is then equal to that of the anode of wall 1. Since the cathode of wall 3 and 5 are at a higher potential than their anodes, these walls do not conduct. In the lower row, right, the anode, this terminal is the anode of your wall. The anode of a wall 2, 4, and 6 are connected together. Therefore, wall 2 conducts when the phase C become more negative compared to these two other phases. Right. This is shown in this diagram. Right. When the wall 1 conduct, when the EA voltage is more positive compared to the EC and EB, right? At the time the wall 1 conduct, and when the wall 2 conduct, when the EC is become a more negative compared to the EB and the EA. So thus before omega t equal to 0 degree, right? And while 1 and 2 are conducting, okay. Just after omega equal to EB becomes more positive than the EA, and while 3 lights when while 1 is zero because cathode is now at a higher potential than its anode. So at this point, right, when the voltage across B is more, right, so while 3 start conducting. Similarly, after the 120 degree, the EC point, right, the voltage across wall C is more, so the wall 5 is start conducting. Similarly, after the 60 degree, the voltage across wall 4 is more negative and therefore it start conducting. Similarly, after 180 degree, the voltage across B phase is more negative, then the wall 6 is start conducting. So this complete one cycle in the sequence is continuously built up. The each wall thus conduct for a period of 120 degrees. When it is conducting, the magnitude of wall current is ID. See here, the walls in the upper row carrying positive current and the wall in the lower row carrying the negative current. The current in each phase of the AC source is composed of the current in the two walls connected to the phase. For example, if we take the phase A, then the I1 and the I4 is there. Similarly for phase B, I3 and I6 is there. And similarly for IC current, I5 and I2 is there. So the average direct voltage for these three-phase bridge rectifier bridge circuits is calculated using this equation. VDO is equal to 1 upon pi by 3. The 1 upon pi by 3, it is a total conduction period of that phase. Okay, voltage, the total conduction period, right? See here, how many cycles is there? Pi by 3 means what? 60 degree. So each will conduct for 60 degree. Okay, because we get the total one phase, it is a 360. जब आप cycle complete करिए, so this is a 360 degree, right? So 360 divided by 6 pulse. So each will conduct for 60 degree. Okay, and therefore we write here PDO is equal to 1 upon pi by 3 integration the conduction period of EAC d theta. So we take 3 upon pi minus 60 to 0 degree EAC d theta, right? So we get this equation. Now what is EAC? As you know, in previous equation, what is EAC? So EAC is equal to 3 upon pi is there, minus 60 to 0. What is EAC? It is root 3 EM cos theta plus 60 degree, 30 degree, right? Cos 30 d theta, right? So simplify this, right? So I'll say 3 upon pi, root 3m is a constant because theta no differentiate, it is a sine theta plus 30 upper limit minus lower limit. Okay, so when we put the value of upper limit and lower limit, you will get the value of VDO 3 upon pi root 3 EM into sine 30 plus sine 30 sine 30 plus sine 30 is 2 sine 30 and sine 30 is 1 by 2. So 2 is cancelled out. So you will get root 3 EM upon pi. 3 root 3 EM upon pi. Now what is the meaning of this video? Right, it is a no load DC voltage. Right, we cannot give the any delay. Right, therefore it is a VD is a DC voltage and zero delay. Therefore it is denoted by VDO is equal to 3 root 3 EM upon pi. So this is a without delay. As you know that the EM is a peak value of line to neutral voltage. So as your RMS value of line to neutral is ELN and line to line is ELN. So there is a one relation between peak voltage and the line to neutral voltage and the peak voltage and the line to line voltage. So EM is equal to root 2 ELN and the EM is equal to root 2 by 3 ELL. So by putting the value of EM in this equation, you will get VDO is equal to 3 root 6 by pi ELN and 3 root 2 by pi ELL. Right? Where ELN is a line to neutral voltage and ELL is a line to line voltage. So this is a derivation of a ideal no load direct output voltage. So now we derive the expression of peak to peak ripple voltage. It's called the peak to peak ripple voltage. Short form is PPR. Right. So the peak to peak ripple for a three phase is if we take the difference in the voltage at omega t equal to 0 and omega t equal to pi by 6, we got the peak to peak ripple. So the equation is like V0 of t at omega t equal to 0 minus V0 of t at omega t equal to pi by 6 is equal to, right, so those root 3 EM omega t છે ને so it's cos omega t એટલે cos 0 minus cos pi by 6. Now what is this? It is your peak PR. Okay, so by simply calculating that we get root 3 EM into cos 0 is your 1 and cos pi by 6 0.866, right? So you will get is equal to 0.134 into root 3 EM. So it is equal to 0.232 EM. This is a PPR. For a 6 pulse. Okay. Suppose if we put the value of VDO, right? VDO is equal to 3 root 3 EM upon pi, and from there you will get the EM, and put the value of VDO EM here, you will get 0.1403 VD. So you get the equation of PPR, right, in terms of EM as well as VD. So this is your peak to peak ripple. So now the wall current relation, right? The second one is a wall current relation. Wall current relation. Okay. So see the diagram here. Okay, the wall current 1, right? It is conduct from minus 120 to 0 degree. That means minus 2 pi by 3 to 0. The wall 1 is conduct, and the remaining period from 0 to 240 means 4 pi by 3, right? The wall current 1 is the 0, right? because the current while 3 and while 5 is conducted during that period. So we can write here I1 is equal to the value of magnitude of wall current, it is ID during minus 122 0. That means minus 2 pi by 3 less or equal to omega t less or equal to 0, and I1 becomes 0 for 0 to 4 pi by 3. Right. So the average value of wall current, so the average value of wall current we can calculate, right? I average 1 is equal to, it is total time period, it is 2 pi, right? So the limit is minus 2 pi by 3 to 4 pi by 3. So it is minus 2 pi by 3 to 4 pi by 3, right? I1 d omega t. Okay. So now put the value of I1, right? So here the two limits is there, okay, for putting the value of I1. So let's here, right, is equal to 1 upon 2 pi, two limits, first of all minus 2 pi by 3 to 0, the value of I1 is ID, I1 d omega t, plus 0 to 4 pi by 3, I1 omega t, d omega t, right? So it is equal to, so it was a minus 2 pi by 3, it is ID, right? So when we put the upper limit and the lower limit, the upper limit is 0, so 0 into 0 plus 2 pi by 3 upper minus minus lower plus plus into ID, right? And this all is the 0, right here. Okay, so this term become a 0. Okay, so you will get 1 upon 2 pi into ID into 2 pi by 3, right? So this is equal to, so this is finally 2 pi cancel out, right? So the I average of wall 1 is equal to ID by 3, because this I 2 pi is cancelled out. Okay, so this is the average value of current. Now suppose you have to calculate the RMS value of current. RMS value of wall current, right? So as you know that the RMS of square is equal to the total time period, it is 1 upon 2 pi, the wall 1 conduction period, or it is minus 2 pi by 3 to 4 pi by 3, I1 square d theta, right? So again put the value of I1 square, theta is your omega t, where theta is equal to omega t, right? So by putting that, you will get 1 upon 2 pi into 0 plus, now I1 square, that is ID square, multiply by upper limit is 2 pi by 3, and again second term is 0, 0 to 4 pi by 3, it is 0. Therefore, we take a 0. So 2 pi cancel out, so it is id square by 3. So 2 pi cancel out, so it is id square by id square by 3. So the RMS value of wall current, it is id by root 3. Right. So remember these things. Okay. It is very useful. So PPR, it is 0.2332 em or 0.1403 video. I average current for valve 1, it is id by 3. Similarly for all the valve, right? So average value of valve current is id by 3, and the RMS value of valve current is id by root 3 for 6 pulse. Okay. So now derive the expression of a transformer current for a secondary side. Transformer current on secondary side. So the current in each phase of the secondary winding of a star connect transformer, it is shown in the waveform here. Current in the phase A is positive when the valve 1 is conduct. When the valve 1 conduct, the current is phase positive and is given by, so the current in the phase A, it is called the IA at time t is equal to the value of current is id, right? So when it is present during the 0 minus 122 0, the valve 1 is phase A is conducting, so it is minus 2 pi by 3 to omega to 0, right? Again it is 0 for 0 to pi by 3, see here, from 0 to pi by 3. The phase current, A phase current is 0. Now again from 60 to 180, the valve 4 of phase A is also conducting, but the magnitude of that current is minus id. So during the pi by 3 to pi, again the phase current is conducting and the value is minus id. And the from pi by pi, from 180 to 240, that means pi to 4 pi by 3, again the A phase current is 0, right? So based on that, we write again two equation. It is a value of is minus id for pi by 3 less or equal to omega t less or equal to up to pi, and the 0 for pi 3 for pi by 3, right? So this is the total conduction of a phase A current, right? So now we put the calculate the RMS value of that. Again the same equation, IA RMS square is equal to the total conduction period, it is a 2 pi, the limit is minus 2 pi by 3 to starting here from 4 pi by 3, so it is a total 4 pi by 3, right? IA square d omega t. Putting the value of this, right, 5 by 2 minus 2 pi by 3 is 0, it is id, 0 to pi by 3 it is 0, and pi by 3 to pi it is minus id, and again pi to 4 pi by 3 it is 0. So this 2 is eliminated directly, is equal to, right, the total conduction period is 1 upon 2 pi, it is 2 pi by 3 into id square because the magnitude is id plus pi by 3 थी 0 अपर लिमिट मूकिए तो plus id square into 2 pi by 3 for minus id, but as it is a square, so it is a positive, and the 0 to into pi by 3, right? So when we do that, that is a 4 pi by 3 id square, right? So 4 pi, so it is a 1 upon 2 pi is there, 2 pi by 3 plus 2 pi by 3, it is a 4 pi by 3 id square. So it is a 2 to cancel out, pi is cancel out, so it is 2 by 3 id square. So this is your IRMS square. So if you calculate, if you want to calculate the value of IRMS, so under root of that, so it is under root of 2 by 3 id. So it is also called the IS. So the current on the secondary side of the transformer, it is under root of 2 by 3 id, where IS is called the current on the secondary side of the transformer. Now the next is the transformer volt ampere rating. Right. So as you know that the conventional volt ampere rating of a three-phase converter transformer feeding secondary current IS and line-to-line secondary voltage ELL to a 6-pulse bridge converter, which is given by T is equal to root 3 ELL into IS into 10 raised to minus 3 kVA. Okay. So as you know that what is the no load DC voltage? The no load DC voltage VDO is equal to, in terms of ELL, 3 root 2 upon pi ELL, and therefore we write, therefore ELL is equal to pi upon 3 root 2 VDO. This is equation number 1, right? So we get T is equal to root 3. Now what is ELL? Pi by 3 root 2 VDO. What is IS? It is under root of 2 by 3 ID multiplied by 10 raised to minus 3 kVA. So by solve this equation, we will get pi by 3 VDO ID into 10 raised to minus 3 kVA. So the transformer kVA rating of a three-phase bridge converter T is equal to 1.047 VDO ID into 10 raised to minus 3 kVA. Where VDO is your no load direct output voltage with a zero phase control, means alpha is equal to 0, and ID is DC output current of a 6-pulse converter. Right. Also, if we write the PD, the direct DC power is equal to VDO ID, then this equation, upper equation of a transformer volt ampere rating is become 1.047 PD into 10 raised to minus 3 kVA. First of all, we derive the equation of peak-to-peak ripple, right? After that, the wall current, average value of wall current, RMS value of wall current, the current transformer secondary side, and the transformer volt ampere rating. Okay, so now the next one is a volt ampere rating of a wall, right? Up to that, we derive the equation of volt ampere rating of transformer. Now, the volt ampere rating of wall. Volt ampere rating of a wall. So the volt ampere rating of each wall is the product of the average value of current through the wall and the peak inverse voltage of the wall. So the peak inverse voltage in terms of DC voltage, it is called the PIV, peak inverse voltage, which is equal to VDO into pi by 3. This is already derived because as we know that the peak inverse voltage is also root 3 EM, right? So we know that, therefore we know that VDO is equal to 3 root 3 EM upon pi. So root 3 EM, so it is pi by 3 VDO. So the peak inverse voltage is pi by 3 VDO and the average current is ID by 3, right? So the volt rating of each wall, for each wall, volt ampere rating of each wall is equal to I average into PIV. So what is I average? It is ID by 3. And what is PIV? It is VDO into pi by 3. So it is, we get 0.349 VDO ID. This is for each wall. So in 6 pulse converter, total number of walls is 6. So the volt ampere rating of all the walls for 6 pulse converter, volt ampere rating of all the walls is equal to 6, because 6 walls is then multiplied by so which is equal to 2.094 VDO ID. And as you know that what is PD? It is VDO into ID. So again you can write 2.094 into PD. So this all the derivations, right, which we see here, it is for without delay. So thank you for that.